If you ask a question today, that what's the most challenging task that humanity has its front? And you ask this question to a politician, you can ask it to a scientist, you can ask it to an environmentalist. Perhaps, in this case, they'll be unanimous. They'll give only one answer, and that answer is that the biggest challenge today is to provide energy for the humanity, particularly for the developing countries where there's a large-scale growth potential, and at the same time, maintain the balance in the environment and mitigate any possibility of climate change. This is something which is really accepted, not just the scientific community, but also politicians. So if you look at the Earth at night, you will see the distribution of electricity used in the whole world. Obviously, it has a reflection also of the population distribution. So it doesn't tell you the statistics. If you come to the statistics, then you will see that you have per capita electricity consumption changing widely from one place to another. It's all indicated there. The United States is not the highest. Norway has the highest because they have a lot of hydroelectricity. It's about 13,000 kilowatt hour. World average being about 2,700 kilowatt hour. India is at a level of 704. But this aspiration of the growing population to have a better quality of life would require more energy. And if you look at not just the statistical figure, but also the real numbers in some cases, even today, about 20% of world population do not have access to electricity. So sometimes, purely by statistics, you cannot emphasize the fact that they have not even 700 kilowatt hour, but 0 kilowatt hour. And in case of Indian population, you can see the number about 300 million people do not have the access to electricity. So what is going to happen in the next 20 years? You know, in countries like India or China, there has been very large-scale economic growth. And all this economic growth can be sustained if you provide energy. So in the next 20 years, if this 8 to 9% economic growth, which has been continuously there in India for last decade or more, if it is there, then you will see that we'll go from present level of about 220 megawatt installed capacity to something close to 800. So four-fold increase in energy. And this would represent CO2 production of about 3 to 4 billion tons, over and above whatever is being done today. So that's the real challenge. So what is the solution? No doubt that the solution comes from the primary energy sources. It is solar, wind, and nuclear. But when we talk of these primary energy sources, they have to be classified into two classes. One is distributed and intermittent. The other, nuclear, which is very concentrated and continuous. It's very obvious to understand that because sun doesn't shine all the day, neither wind blows. But the nuclear has a very high capacity factor. And if you look at the kind of distribution, you require about 5,000 square kilometer of area to get a 10 gigawatt, 10,000 megawatt installation by wind. Solar about 400 square kilometer, whereas nuclear can do the job in about 2 square kilometer. Look at the average capacity factor. Capacity factor in wind and solar is about 20 to 25%, whereas in nuclear, it has been proven. It's a technology which has been proven, and it's over 90%. The process of nuclear fission, I'm not telling anything new to this audience. You all know about what is nuclear fission. You have a U-235 nuclei, a neutron comes, it becomes 236, an unstable nucleus, breaks up and provides energy and neutrons. Please also give the emphasis to the neutrons that is created, because without this, it is not possible to establish a chain reaction. And one very important and simple fact to remember is just 1 gram of uranium-235, if you burn in a day, you can support 1 megawatt installation, 1 megawatt day energy is produced. And this is how the whole chain reaction proceeds. And everywhere you see that most important point is the number of neutrons that are generated from every single fission process. Problem is that uranium-235, if you look at just that nuclide, which nature has given us, it cannot really sustain the nuclear energy also for a long time. So the solution remains that is it not possible to utilize the other part of natural uranium? Natural uranium contains less than 1% of U-235, but remaining 99% plus is uranium-238. And that gets converted into plutonium, which can be burnt again Same way, the other element is thorium, which is 232. If it takes one neutron, then it goes over to uranium-233, yet another fissile isotope. So the moment we consider not only uranium-235, but also the uranium-233 and plutonium-239 are our fissionable, burnable material, then you'll find that the energy stock that the world has is really sufficient for sustaining energy supply, not just few centuries, a few millennia. So this was the hope of the first generation nuclear scientist who has worked in several countries in the 50s. But now, because of the many other issues came up, the nuclear program has slowed down in several countries. But again, there's a revival of interest, particularly from the point of view of thorium utilization. Because thorium is very abundant, it's 4 times more abundant than that of uranium, and thorium is also very easily available, like the example that I'm showing here. It's available as in the beach sand in Kerala, and there's a huge reserve of thorium in India, in many other places in Scandinavian countries, and the stock of that is typically 4 times that of uranium in the world. But one has to accept the other important issue about the fuel cycle. If we use the spent fuel which comes out of the nuclear reactor as a waste, then we are not tapping the full energy of it, energy potential of it. It's only less than 1% of that energy potential has been used. But the moment we do a closed fuel cycle, where the spent fuel is reprocessed, from there the fissile and fertile is again used back in the nuclear reactor, then we can multiply the total energy usage. But more than that, it also handles yet another major issue, that is about the nuclear waste. When you talk of nuclear waste, this is a real technological problem associated with the nuclear energy. Because you generate nuclear waste which is of a very high radioactive life. Here we are plotting the radiotoxicity as a function of time, and you can see that the natural level of radiotoxicity of natural uranium, which is indicated by the green horizontal line, the total level of that comes down to the same level after about 200,000 years. It's a very long time. Human history is only for 6,000 years. So who takes the responsibility? One generation takes the responsibility of generating that waste, which will live for 200,000 years? Obviously not. The answer to that is, again, if we take out things like plutonium, americium, curium, and burn them out in another reactor. So the closed fuel cycle not only provides you more of the energy supply, but it also takes care of the waste. Coming to the thorium, recently, in fact, in literature, in internet, everywhere you find there's a tremendous interest in thorium reactors. Why? Thorium can be used in different types of reactor. It can be in solid fuel reactors, it can be in molten salt reactors, and also in accelerator-driven subcritical systems. If you are talking of an established technology, robust technology, which has worked for many, many years, decades, even now, 14% of total electricity generation in the country, in the world, is from nuclear. And you can see that it is possible to do in conventional reactors. You know, Carlo Rubbia, who was the director of CERN, has actually predicted many, many years back that you can, in fact, use thorium in the conventional reactors. So India took the effort of designing, which has gone through many international reviews, and we know that it's possible to design a reactor which is very safe, because here, everything is passive. That is, all safety mechanism does not depend on human intervention, neither external power. Because whenever we talk of nuclear power, you remember of the incidents in Fukushima. So we have to think not only of use of thorium, but also that how natural circulation, which is by just the thermogravimetry process, in that you can take out the heat. And these kind of reactors can burn uranium plus thorium, it can burn plutonium plus thorium, it can also burn low-enriched uranium and thorium. Look at that, it essentially can burn the spent fuel of the previous generation reactors. Coming to the molten salt reactor, it's a very interesting concept. The whole reactor core, the fuel, everything is in molten condition. We are all worried today of the meltdown accident, that inside the core of a nuclear reactor, things will melt down and will cause problem. But here, everything is already molten. So there's no chance of a meltdown type of a process. That fuel actually circulates through, and it goes through a reprocessing plant. So it takes out all those which are poison for the neutron, and it also puts in all that other fissionable material which are depleted, and that can be pushed in. So it's something where there's, in terms of today's nuclear reactor, practically no generation of long-lived isotopes. So waste problem is tackled. It is also very interesting that it has other many interesting features of safety. People say that you can even in your backyard in a reactor of this type. Why? Because these reactors can be made very small. Secondly, it's all passive. Even if there's any kind of a departure from the normal operation, it will come back quickly to the safe system. Minimal waste is efficient because you are working at a temperature of about 650 degrees Celsius, much above the 300 degrees Celsius of the water-cooled reactors. The other idea is also extremely important. This is again something which has been toyed with in this center in CERN, as well as in many other centers in the world. It's not a technology which is developed, but the science part of it is fully established. What it does is that, I mentioned to you earlier, that what is most important in the nuclear energy or nuclear technology is keeping the balance of these neutrons. If you don't have excess neutrons, you just can't convert all that fertile resource that nature has given us into fissile, like thorium or uranium-238. Here what one does is bombarding by very high energy particle. A giga electron volt proton can strike a nucleus and again can make the nucleons inside the nucleus boil up. In that process, you can see the spallation, which means essentially boiling. Neutrons shoot out from the nucleus. Earlier referring to that only 2 neutrons come out. In this case, you may get even 20 neutrons for a single spallation process. And these neutrons can convert the fertile to fissile. These neutrons can also couple with a nuclear reactor around it. So the basic structure of accelerator-driven system will be having a kind of a core in which the target material of heavy metal, in which you'll be having incident proton of 1 giga electron volt coming from an accelerator, and see the inherent safety feature of that. If the accelerator is switched off, the whole reactor is switched off. And then this coupled system, an accelerator and a reactor, can indeed use thorium without any reprocessing. That's yet another big challenge, and it's possible. We have a program which is running for nearly 40 years now, and we start with natural uranium. Our present generation reactor, our uranium fueled, produces energy. But we also produce plutonium, which is being pumped into our fast reactor. And once in the fast reactor, you get many more neutrons than in a thermal reactor. It's possible to convert thorium to uranium-233. And that is our future, where thorium can be converted into uranium-233 and can make nuclear energy a sustainable form of energy. So for the stage 1, it is a power generation and building the fissile inventory for the secondary. Stage 2, expanding the power program and making more of U-233 inventory. And third stage is burning this. Now, all this have been done. In the first one, we are threshold of the second stage ready. Because natural uranium-based reactor, we have been running for some time. This is producing plutonium, which is going into the first reactor. The world's largest commercial fast reactor will be operational in India next year. It's a 500 megawatt electric. And we also have been running from 1996 a thorium uranium-233 reactor. It's interesting that all these 3 reactors are located in one place in India, very close to Chennai, the place called Kalpakam, where you have a thermal reactor, we have a fast reactor, we also have a small experimental U-233 burning thorium U-233 reactor. So in fact, it's a great opportunity for me to even invite you to have a visit to India and just go to Chennai and see all the things in one place, which is not there anywhere in the world. With that, I thank you all.